We switch to the second guest speaker of today, who is Arianna Menciassi from Scuole Superiore Sant'Anna, Pisa in Italy. And I think, hello.
Yes, hello, good morning, good evening, good afternoon for people in Japan. So thank you very much for inviting me to give this talk. I have to say that, can you hear can you see the slides? Okay, that's better. Okay, so thank you. I have to say that I was a little bit hesitant to accept this talk because my question was maybe what I can present is not so adequate for people interested in topics related to artificial intelligence. But I hope that there are some materials that can be useful, at least to be, to be used as key technologies to be considered also for problems related to artificial intelligence, embodied intelligence, and so on. So, which are the motivations behind this work? So, maybe you are aware that there are some technologies for tissue engineering, so for growing tissues. And these technologies for tissue engineering, they are related to culturing cells, to scaffolds, to differentiated cells, and so on. And they can be applied in fields that are different from regenerative medicine and from tissue engineering organs. And this field can be the field of biohybrid components and machines. So technologies for biohybrid actuation, biohybrid sensing can be also applied for example, for rehabilitation, for organ recovery, for neuroscience. You can see here some pictures, just very qualitative, to demonstrate possible area of application of biohybrid components and biohybrid machines. So the outline of my presentation today is the following. First of all, I would like to enter you in the field of actuation and sensing in machine design in general. So I'd like to illustrate some features and advantages of natural actuators and natural sensors, then explaining which are in the state of the art the different attempts to develop biohybrid actuators and biohybrid sensors, which are the problems, the main problems to solve for biohybrid construction, and some possible steps towards biohybrid elements, especially in our group and in other group connected to our institute. So, when you consider future machine, one of the main bottlenecks, especially for people working more on the hardware part, there are many bottlenecks, maybe also for control, for sense interaction, but in terms of building a machine, we have one main bottleneck that is the actuation. On the other hand, actuation is a function that is essential for any artificial and any living machines. Actuation allows the movement, interaction of the machine with the surrounding environment. And if you consider a large machine, for example, an industrial robot or also a humanoid, they are normally characterized by a lack of flexibility and a lack of lifelike movement. And also, if you consider micro machines, for example, you have many problems of scalability. I have to say that some technologies exist for actuating micro machines, also coming from nanotech. But you have a huge problem of scalability and the hierarchy of forces. So the bottleneck of actuation is a general bottleneck at all sides, in a sense. So sorry if the movie are not so fluid, but I want just to demonstrate with the comparison between these two movies that at least for large machine we have a lack of flexibility and lifelike movements if you compare, for example, the dancing now robot and the professional dancer Roberto Bolle. So the reason of the difference between the robot and the human is that in the first case you have basically rigid constitutive elements and joints, you have no compliant actuators, and a sort of centralized intelligence. That is totally different from the approach of a dancer, of a human motion, where you have flexible constitutive elements and joints, compliant actuators, because our muscles are compliant, and the intelligence that is distributed, embodied, let's say, in the body. So if you want to have a more, I'd say, didactic approach to actuation technologies, you have to consider different options that are available. And you can, how to say, compare these different technologies by considering a graph like this, where you estimate the maximum output force or the maximum output compression in Newton, so it's a force, versus the maximum stroke. And so you can report in this graph all the different families of different actuation technologies. So let's see in the yellow circle, let's analyze one possible option for actuation technologies: piezoelectric actuators. Maybe you are aware of some piezoelectric actuator device. Normally, piezoelectric motors and piezoelectric actuators are able to convert, to change the shape of the material, responding to an applied electrical field. They can be very, very fast. They can be very precise, for example, for high precision tasks. In the second movie, there is a sort of moving slider using for micro positioning. As I already mentioned, they are very fast. They can be very fast. In fact, maybe you have the experience of ultrasonic motors that are based on a sort of engineering of piezoelectric actuators. But the main problem is that the stroke is extremely limited. So they are good candidates, but with this very important limitation in terms of stroke. So you cannot take a piezoelectric actuator with the size of your muscle and expect a deformation of 30 or 40%. The deformation is no more than 1,000, one part of 1,000. So let's consider another technology that is very used in also many robots, also for industrial automation or for many different applications. It's an actuation technology extremely versatile. Pneumatic actuation in the yellow circle again. So also pneumatic actuators are very spread in many applications. The principle is that they convert the energy, typically in the form of compressed air, into mechanical motion that can be linear or rotary. In the first movie, you can see the typical McKibben actuator, where you have a combination of materials with a specific configuration, a pneumatic actuator, to obtain some, let's say, artificial biomimetic muscles. In the second movie, there is a surgical robot, very, very precise, very thin, and actuated by air. So pneumatic actuators are a good compromise between force output and stroke. They can mimic very well some specific muscle features, but which is the problem? The problem is represented in the last picture. The main problem is that they need an extremely bulky energy source. Let's consider some examples in sensing technologies. In future machine and also in ordinary machine, we have an additional bottleneck that is sensing. Natural sensing, for example, the sense of touch, is performed normally by compact, robust, self-contained, multi-response mechanism. And so, for example, by using your hand, you're able to perceive the softness, the temperature of the body, and so on. On the other hand, there are many different technologies for artificial touch replication, but they involve many limitations. In the bottom picture, you see a very large number of wires, and this is just an example to demonstrate that when you have many tactile units, the wiring problem is one of the main problems from the implementation and integration viewpoint. So after this general introduction about actuation sensing problems in machine design, let's see the feature and advantage of natural actuators and sensors. So why complicating so much our life trying to use the biological entities to develop biohybrid constructs? So the muscle is something with some unique properties. You can see in the movie it is extremely slow, and it is slow because it's really slow. It is not slow for the teleconference. In the movie you can see the typical process of muscle contraction. So natural muscles rely on a finely regulated actin-using contractile machinery. That is what is demonstrated in the movie. This machinery has a modular architecture, and it is optimized by millions of years of natural evolution. I took this example from a paper published by Professor Barry Trimmer, comparing the evolution of cars in 25 generations of different cars, starting from the end of the 19th century until 4 years ago, and the evolution of mammals, starting from 56 million years ago up to today. So in the first case, you have a very impressive difference between the first car and the recent car, and you have just 25 generations. With more than 56 million of generations, it's not impressive if the animals, the mammals that you now are so different from the first animals, and so it's not difficult to understand that the machinery, the evolution contributed to improve very much this actin-using contractile machinery. Which are the key skeletal muscle features? For sure, the muscle is back-drippable, and this is something that is not so common in actuators. Not all actuators are back-drippable. You can control the stiffness in the muscle. You have a very good efficiency in transduction. You have properties of self-sensing and self-healing. Normally, if you take a motor and if you want to add sensing capabilities, you have to add encoders, for example, for a sort of self-sensing. This is something that you don't need simply in the muscle, because there is this ability in self-sensing. The fuel is chemical. It's very good because it is also very silent in during its working, and they have an anaerobic transduction efficiency. So 1,000 joule per gram of glucose per gram of sugar. So if you take the previous graph with all the artificial actuators, you observe that no artificial actuators are able to reproduce the behavior of muscle integrated series elastic components, which are thought to give rise to many of the lifelike characteristics of animal movements. So muscles outperform in this sense many, basically all the traditional artificial actuators. This talk is more focused on actuators, but I like to make also it more balanced, also discussing about not only actuators, but also sensing, biohybrid sensing technologies. So I am not an expert of the human tactile sensing system, but I took some pictures and some slides from books and other colleagues. So the tactile sense is a complex architecture with no localized single sensory organ. You are able to sense altogether many different features in terms of temperature, shape, force, friction, gain, and so on. This spatiotemporal tactile information is encoded as spikes of action potential transmitted to the central nervous system by means of tactile units, and this is something not easy to be replicated with artificial machine. In many cases, when you buy something and people claim, okay, there are tactile sensors. In many cases, these tactile sensors are not tactile sensors, but they are force sensors. So they are able just to provide an haptic feedback, so to have a sort of measurement of the force, not of all the different parameters that a natural tactile system can provide. And we have different sensory endings to sense different mechanical stimuli. So, we have seen what we have as regards traditional technology. We have seen which are the key features of muscles, of biological muscles and biological tactile sensor systems. So, how obtaining bio-like behavior with the technologies that we have available? One possibility is to design a sort of smart or soft smart mechatronics body. I took this movie from a colleague of mine, Cecilia Lasky, Natasha Katie, working on the octopus robot, and they are very nice because they have tried to replicate the operation of the real octopus arm, and in a very clever way they were able to put together traditional actuators, shape memory alloys, together with some smart materials, a smart design, a combination of different compliant sleeve around the actuators and so on. So the design is very nice, very complicated, and totally artificial. Another solution is to use, for obtaining a bio-like behavior, is to use biomimetic actuators, based on smart materials. So if you take my original graph, there are many different actuators, and there is a family of actuators called electroactive polymers, or also ionic polymer metal composite, and these are some polymers that normally exhibit a change in size or shape when stimulated by an electrical field, and they are used for biomimetic devices. So you can see here some examples of biomimetic devices. Very interesting is the last flying fish in the last movie. And in all these cases, the researchers tried to integrate these materials that are active, but that are also used as structural material for the machine. So, this is basically the state of the art when you try to replicate natural muscle, a natural sensing system by using traditional artificial technologies. So what I mean for biohybrid approach to actuation and sensing? The state of the art is quite variegated in this field. So the first example that I found reported in the literature was based on devices operated by explanted living muscle cells. So in this case, you can see a sort of mesoscale fish, about 10 centimeters in length, that is a muscle-powered swimming robot with an autonomy of 4 hours, with a speed of about 0.3 bottlenecks per second. And the working principle is extremely simple, where in the first schematics, where you see the letter MM, they are some piece of muscles taken from a frog and integrated in this robot. So by actuating with electrical energy these muscles, they are taken from a frog, so they can survive in specific in specific environment. They can move the tail, and so that the robot can swim. The main drawback for this system is that, first of all, you need to sacrifice vertebrate animals. The second problem is that the lifetime is extremely limited because you have to explant the muscle. So you remove all the other functional structures, so you remove the vascular network, and so the tissue very rapidly degenerates. And possible actuators, architectures are limited to what you find in the nature. So if you start from the frog, you have the architecture of the frog leg, and so on. So more advanced solutions that you can find in the state of the art are represented here. So there are people using some microfabricated structures. So if you know the field of MEMS, microelectromechanical system, let's think about some small lithographic structure that can be coupled with some, I'd say, biological glue with self-beating cardiomyocyte cells taken from animals. And as you can see in the movie, you can obtain a nice walking machine with a speed that can be around 40 microns per second. Very, very small, because you have to use a couple of cardiomyocytes together. So a cardiomyocyte is no more than 10 microns in size. But the working principle is very soft, bio-like, and it seems working very well. The problem with the previous example is a problem of scalability, because if you work with a few cells and if you cannot, how to say, build a real tissue, you can operate just very small, very small devices. So another example of a mesoscale device with scalability potentials is represented here. This is a nice work published 7 years ago on Science by Feinberg, and he was able to pattern cardiomyocyte on soft materials, PDMS materials, and by using this specific pattern he was able to obtain a sort of controllable motion of PDMS structure. As you can see in the movie, so some rolling architecture and so on, by using not only one cardiomyocyte, but many cardiomyocytes with a specific disposition. And by using the same approach, there is a group in Japan, for example, fabricating real devices, for example, micropump, micropillars, similar things, by using a sort of sheet of cardiomyocytes that are, for example, integrated in pumps for obtaining a sort of peristaltic motion of a pump. Another possibility is not using cardiomyocytes, but using some self-beating cells that you can find in insects. That are some insects with a sort of dorsal ventral tissue that is self-beating. And the nice thing is that in this case you can obtain very, how to say, microscopic motion. And by using insect in comparison of mammalian cells, you have the advantage of an operability at room temperature, because you know that insects don't need to stay at 37 degrees. So it's a sort of advantage also in terms of general use of these cells. And for this reason, for example, self-beating insect cell-based devices were developed. This is a nice case of a gripper, a compliant gripper, where the actuators for pulling the gripper is obtained by using this self-beating cell encapsulated in a sort of flexible bioreactor. So, which is the problem of self-beating cells? The problem of self-beating cells is that they are self-beating. So you cannot decide when stopping the cell or when activating the cell. There is the possibility, let's say, to tune a little bit the frequency, for example, by using some chemicals. But it's something different from the approach that you have with a motor, that you decide when switching on and switching off. For this reason, a more promising solution is to use skeletal muscle-based devices. So not coming from the earth that is self-beating, but from our muscles. And for example, in this work published on Lab on Chip, researchers were able to fabricate film with some patterned skeletal muscle-based device, and with the ability to stimulate them by using electrical field, as in our real muscle rubber limbs, for example. You can see here it's very small, the displacement, but you can see here this strip of muscles with this arc structure. The arc structure are with the electrodes, and there is a very small motion, few microns, sorry. A very small motion, few microns of the cells of the muscle strip when activated by the electrodes. Another interesting work in this field was to try to change the triggering for actuation. So electrodes are nice, but they are quite complicated to be integrated. So it is very nice to have a sort of triggering completely wireless. And this is something that was done with an optogenetic control of engineering 3D skeletal muscle bioactuators. This is a work published by Ariasada at MIT. So basically, it was able to grow some muscle cells, and they modified optogenetically these muscle cells so that this muscle cell could be triggerable by a laser beam. So you can trigger specifically specific fibers of your construct. So this is in the direction of maximizing the controllability and trying to answer requests of scalability. I think it's the same movie. Oh, okay. This is a sort of construct with two pillars, and where you can see the blue square, it means that you are activating the muscle. In this case, it's clear that you can, for example, modulate the frequency, because it depends on the frequency of the triggering of the laser. So let's come back to our original graph. So I'm achieving the same performance of natural muscles. I decided not to bore you with calculation, but I can say that what you have seen until now with the cardiomyocyte-based device and skeletal muscle-based device, if you take the maximum stroke and if you consider the maximum output force, you find the yellow and the blue, the light blue circles. So basically, the performance are not so brilliant, especially if you compare with the muscle that is in the top right of the graph. So how we can, with the same ingredient, how we can make this jump? So from very poor, promising but poor performance to very good performance as in the muscle. So for optimizing the device behavior, for sure modeling can help. Modeling this field is extremely complicated. It's a multi-scale and multi-purpose modeling. For example, you have to model nonlinear, hyperelastic, and cell-basic materials. You have to model combined physical effects because you have the triggering by electricity and some, how to say, response from the substrate and so on. You have to model also at the micro-nano scale because the cells can adhere to the substrate thanks to some specific bindings mediated by proteins. So it's a quite complicated modeling starting from the nanoscale up to the traditional scale. If you want to compare with to make a comparison with the Biohybrid tactile sensing system, which is the state of the art. I have just one slide about Biohybrid tactile sensing system, but I have to say that also for tactile sensing system, there are several examples in the state of the art. For example, there are examples of MEMS-based capacitive tactile sensor covered by tissue engineering epidermis based on keratinic seeds that are taken from the skin. So the idea is to have a pressure sensor where a component is a biological component. Another example is in the second picture. It's a tactile sensor based on a plasmodium that is visible at the naked eye. And so, and this plasmodium is able to detect different loads thanks to differences of surface potential measured when you apply a different load. So in this case, this plasmodium were integrated in artificial devices. So this is basically the state of the art. So which are the problems to solve for Biohybrid construction? We have the state of the art, we know the main problems. So let's try to make a sort of didactic list of which are the main problems to solve. So, I like to present the problem of biohybrid actuators and sensor with these slides with the pieces of a biohybrid puzzle. Because there are several pieces to consider. First of all, in terms of living and non-living interface, you have to consider the development of engineering substrate where growing your cells, the choice of suitable cell lines, because not all cell lines are adequate at the same level for this application, and the maximization of cell contractility. In addition, there are other ancillary technologies to be considered. For example, if it is possible or not, easy or not, to integrate microelectrodes and control system. The functional interfaces for transmitting the force, we have not only muscles, we have also tendons. So the problem of developing artificial tendons, the assembly of many contractile units, so the problem of scalability, and the problem of keeping this construct alive, so to develop some bioreactors that are miniaturized and flexible. So the analysis from now to the end is more tuned to biohybrid actuators, but many pieces of this puzzle can also stay for biohybrid sensors. So in terms of suitable cell lines, we have seen that there are several options. Primary cardiomyocyte that are self-beating, primary insect dorsal vessel cell that are still self-beating but at low temperature, immortalized skeletal muscle cell lines, primary skeletal muscle cells, insect embryos deriving myotubes, and quite recently stem cell or induced pluripotent stem cell, because in a sense you can start from an embryonal cell and you can grow this better cell, the best cell that you need for your actuation solution. In all cases, the best solution is to have a co-culture of different cell types. What I want to say is that, okay, you can fabricate a small actuators with a few cardiomyocyte explanted from an animal, and it works. But if you want something reliable with a data sheet that can demonstrate many cycles of your actuators, you need to replicate a little bit the structure of the muscle, for example, with a sort of bed of fibroblasts between your substrate and the cells. The second piece of the puzzle is the maximization of cell contractility. For sure, if you take cells and if you put cells on an artificial substrate, the contractility cannot be the maximum available in natural animals, in natural environment. For this reason, there are some solutions coming from tissue engineering, from biology. So it's possible to make a combination of chemicals and physical stimuli in order to improve the contractility of cells. Or it's also possible to make some genetic modification of cells, because please consider that this is not for tissue engineering, this is for an artificial use. Also, modification of cells is something reliable and possible. Or you can stimulate, as we do, the construct with stimuli based on nanoparticles that are reactive when stimulated inside the cells. As regards the other technologies, embedded microelectrodes. When you have to develop embedded microelectrodes, you have to think about electrode integrability, biocompatibility, and long-term stability. Long-term stability is a real issue, because normally you operate at 3, 4, 5 volts in an environment that is a liquid environment, and in this case, you have some problems of electrolysis. In addition, you have to avoid cytotoxicity. In addition, you have to avoid the delamination of the electrodes, because you are putting your electrodes in some substrate that are flexible, and so you can have many problems of delamination. As regards the functional interface to transmit force and power, in the state of the art you can find some tendon-like structure, also based, for example, on silk or some biomaterial, to connect the actuator with the external world. You don't know just a system moving to take some picture with a microscope. You need something moving and moving something other. So you need a real actuator. And for the functional interface to transmit force and power, you have to design not only the active part, that is the muscle-based device, but also you have to take care of the passive mechanical feature of your system. Also, the bioreactor is important because you need to keep the cells in a controlled environment and to keep them alive. And so you need a bioreactor with tuned mechanical feature, not hampering actuator contractions. Another problem, if you want to scale up your actuators, is to assemble single contractile units. And it's not only simple assembly just to replicate the muscle, but you could also think about how to say very variegated possibilities of different architecture, not to replicate, but also for outperforming natural solutions. So if you want an actuator that is able to elongate in a specific way, maybe you can assemble the different contractile unit in a different way in terms of shapes, architecture, corresponding to specific tasks. Okay, so I want to conclude this presentation by illustrating some steps toward biohybrid elements. Unfortunately, we have not yet fabricated a nice actuators just based on muscle cells, but we are trying to put together all the different key enabling technologies. So we have some examples where we used muscle cells with 2D polymeric films. So we developed for also different application compliant substrate based on PLLA material, very flexible, very robust, but also very flexible, able to be injected, for example. And we put some cells, contractile cells, on this PLLA substrate. This is a movie without any, let's say, any magnification. So it's about 1 millimeter times 1 millimeter. And in this case, you have simply some cardiomyocyte on the film and able to make a very robust contraction of the film. The problem in this case is that we have problem of stability and low differentiation. Another attempt in this direction is to use again a 2D matrix, but with not only muscle cells but also co-culture, so also fibroblasts, and trying to amplify the contraction. So we developed different substrate, in this case based on polyacrylamide gels, and we put, you can see in the picture, we have some grooves. These grooves are used to grow the cells with a specific orientation in order to have not a disorganized but a very organized contraction in a specific direction. The thickness and the young modules of the substrate is optimized for respecting the young modules of cells. We grow the cells on this substrate, very, very well oriented. And we put in also some nanoparticles that are piezoelectric nanoparticles in the medium. Because by using these nanoparticles that are piezoelectric, we can exploit indirect convey of physical stimulus. So, for example, we use ultrasound. With the ultrasound, we stimulate the piezoelectric nanoparticle. This piezoelectric nanoparticle generates electrons that can stimulate the growth of this cell. So, without entering the details, we use these nanoparticles that are based on nanotube with boron and nitride, and we stimulate it with ultrasound that are mechanical wave. What you can observe is that this is the expression of different genes, and the blue line is where you have a co-culture stimulated by ultrasound with boron nitride nanotube. And I have put a circle a yellow circle around this gene that are active, myosin, and other genes related to the motion that are more expressed when you have this stimulation with ultrasound and nanoparticles. So this is just an example to demonstrate that we can combine in a synergistic way different solutions in order, for example, to maximize potentially the contraction. And finally, we try to go from the 2D to the 3D construct. So we decide to fabricate some 3D matrix and to put cells with the idea to put cells in this 3D matrix in order to have a real muscles, not different layers to be peeled up. So we developed a sort of rolling technique by using microfabrication technologies. And so basically at the end of the story, we were able to have a rolling technique with some grooves where putting cells and some pillars to separate the different layers. We are still in the process to put cells in this construct. You can see the same imaging of this sort of skeleton of the muscle, let's say. And what we are trying to do is a sort of modeling, for example, for the moment of the actuator contraction. So we tried to put a model of the force exerted by cells, by different cells, myotube and cardiomyocyte, and this construction in order to optimize the behavior. As regards the second part of my talk, but this is just one slide, we are also in the process of designing a new Biohybrid tactile sensor. We are using cells that show strong mechanical transmission by means of a specific sensitivity area that is based on a primary cilium. These cells are taken by kidney epithelial cells. And we fabricated a sort of environment for growing the cells and for applying load. And we obtained very nice results in terms of tonic response observed during a mechanical stimulation. So now we are trying to optimize the system in order to have a real tactile transduction system. Sorry, because we have some problem with our. You can see me and the presentation also. Okay, thank you. So let's conclude my talk with some consideration. Try also to link a little bit more my talk to the typical topics that are investigated during and approached during the ShanghAI lectures. So for sure, what we can say is that we are using very much contribution from tissue engineering. So for sure, biologists and medical doctors can help us very much in our challenge in terms of advanced scaffold for skeletal muscle tissue engineering, and in terms also of nanomaterials and methods for cell engineering. On the other hand, we have been approached by people working on tissue engineering because we can contribute also to tissue engineering in terms of advanced tools for simulation, monitoring, maintenance of cell and construct, in terms of robot-assisted micromanipulation solution, for example, for peeling up different layers or different construct with cells. But the nice thing that I was not aware at the beginning of this story is that it seems that this activity on biohybrid components is also interesting for people working on neuroscience. We were contacted quite recently by neuroscientists working on the homeostasis of the living of the human body. So Biohybrid system offer a powerful approach to cognitive system based on what the neuroscientists say, and more specifically to biohybrid embodied cognition. So nature has built the apparatus of rationality not just on top of the apparatus of biological regulation, but also from it and with it. Simply speaking, we were contacted by this neuroscientist in order to prepare some biohybrid tissues, biohybrid actuators, to be modified, to be tuned in order to understand the abilities of recovery of homeostasis for this tissue. Starting from the tissue, let's say extrapolate until the eye level, until cognition. So this concludes my talk. I want to thank you for the invitation and some colleagues, PhD students, other collaborators for working with me on this topic.
Thank you very much. So I'm sure there are many questions. Please raise your hand.
Maybe not easy because the activity is quite far away from the typical, let's say, the typical topics of this lecture.
Well, if I can raise a comment on this comment by Arianna, ciao.
Hi.
Is that actually it's not off topic because we more or less push the idea that we think with our body, and we have highlighted many times that we have limitations in mimicking the very different paradigm of natural intelligence into robotics because we don't have, for example, the proper actuators and the proper sensors. No? So I think it's for first very interesting. The point is that the approach of these lectures on AI is very body-oriented. So, I mean, it's not symbolic, good old-fashioned AI. In that sense, your thought is very, very welcome because so it's not by chance we invited you. But because we need to know, so since we have this long-term objective of redesigning robotics for soft embodied intelligence robots, working on actuators is part of the job. So, and knowing from people like you where is the frontier is important also for...
Yes, Fabio, you know our group, and so we didn't start from biology because there are no biologists with us. So we started from the original motivation. So the lack of good actuation technologies, not only for robotics, but also at the small scale. Personally, I work on miniaturized robots, also for medical application, and in all cases, our bottleneck is the actuator. So we started from this need. And the nice thing was that what I learned during the story is that there is already much technologies developed in the biological labs. Very nice key enabling technologies, but maybe there is no collaboration, not because there is not intention of collaborate, but because we belong to different communities. But there are very good group working on biology that have all the let's say, all the stuff to develop this muscle construct, but maybe for different application. Or, for example, they are very good for tissue engineering of liver, because it's something more related to the health of people. So in many cases, you have to replace the liver, the kidney, or the epidermis, but not a piece of your limb. But there are really many technologies already available in a sense. And also I was impressed by the many technologies for already available for maximizing, for example, the contractility. Very simple receive, kitchen receive for maximizing the contractility with an approach that is not the engineering approach, but in an approach that is very biological based, but that can be very effective if you can use and for your aims and purposes.
Yeah, I don't know if, well, when I will leave the floor to other questions, because I think that something which emerges from your presentation is that as we try to build a robot which mimics the natural intelligence, no? The natural robots, the animals, we go into a situation where we have a kind of make or buy issue, meaning should I develop an artificial solution based on nanotechnology, or should I use an existing biological structure and adapt it? I don't know what you think about that. No? So it's analogous to the make or buy. You know?
Yes, so basically I think that the most impressive result in this field was the first fish that I demonstrated with the muscle taken from the frog. And so for a demonstrator, starting from a real muscle already fabricated is the best solution for a demonstrator. Our idea was to develop an actuator that you can buy as you can buy a motor in a long-term vision. So something that you can control in terms of actuation, geometry, architecture. And for this reason, we were motivated to start from the scratch, to start from the acting using machinery and to try to grow up with the scalability.
I have many other questions, but
maybe I can raise another question. So you showed many fascinating new inventions on material properties, and which are almost superior to biological systems. How far is energy still a problem?
It depends on the actuation solution. At the moment, if you consider let's say a film with some cells and films, the actuation based on electrostatic fields is still something totally, let's say, totally artificial. So you have some electrodes and a small battery. Basically, you need just a trigger because the real fuel comes from the medium, from the culture medium. So if you want to obtain 3 joules of energy, you don't need to spend more. You need the electrostatic force just for triggering. Because the muscle is alive, and so as if you have the culture means with sugar, with other nutrients, the energy comes from there. It's the same as in our body, let's say. At the moment, there are many limitations in terms of flexible bioreactor, and so for this reason, some of these actuators are battery powered for generating the triggering. But just for generating the triggering.
Any more questions? Maybe locally here? Any questions? No? Any questions in the global world?
Hola.
Okay, then let's thank the speaker again. Thank you.
Hola.
And well, Fabio, I think we can.
I have a question.
I think there is a question.
In Madrid?
Can you hear me?
Not very well. Try to speak.
It's slow. Okay, I try to speak slower. My question is, when you have this kind of elastic material, isn't there a problem with kinematics? I mean, like since you don't have a rigid bar, do you have a problem knowing where the actuator is?
So the question is if, okay, we have the elastic substrate.
Yes.
And you, the question is, where is the actuator? What do you mean for where is the actuator? So, yeah, sure. Yes, we have not yet approached the problem of kinematics. For sure, this is, and I was quite fast in this topic. The problem of controllability and kinematics is a huge problem related also to the difficulty of modeling. Because the modeling, it's not only the problem of the elasticity of the substrate, that is already a problem in terms of kinematic modeling. But that is the problem is that you have a multi-material with a many different, I'd say, layers. So you have the elastic substrate, then you have some proteins that you have fibroblasts and finally some other muscle cells. So in terms of kinematic modeling, it's quite difficult to be performed. In principle, the idea is that you should work very much on, let's say, on-off actuation of single contractile unit. So basically, you could think that the overall actuator as a combination in a geometry that you know of on-off actuators that you can switch on and switch off. And in this case, it's a sort of binary, let's say it's a sort of binary robotics problem. So even if you don't know very precisely the kinematics of the single film, for example, it is also possible that you can model the film simply as on and off, and then putting together in a specific geometry the different films, you have the overall behavior. Try to think about to the size. So the contractile unit is very small. Also in nature, the actin moving on the myosin is something on-off. It's just a step. You don't control the step, but it's a sort of stepping motor where you control just the end point of your step, not in between, because of the size.
Okay, thank you.